In this problem, our task is to find the value of C such that V of t and I of t are in phase. And we're going to use our problem-solving strategy entitled Basic AC Analysis, where what we're going to do is we're going to convert this circuit over to the frequency domain, and then we'll perform the analysis in the frequency domain. If we take note, the radian frequency here is given as the source, so there's omega. It's 500 radians per second. And to do this, we're given that, and let's now draw our circuit. And for the moment, I'm going to keep everything, all the impedances, it's symbolic. So here's our circuit. So we note our current was 2 cosine 500t plus 25. That becomes 2 at an angle of 25. The admittance of our resistance is 1 over R. The admittance of our capacitor is j omega C, and the admittance of our inductor is 1 over j omega L. Now, let's calculate the equivalent admittance. So, Y will be 1 over R plus j omega C plus 1 over j omega L. Now, if V of t and I of t are to be in phase, then, let's see, for V of t and I of t to be in phase, then Y would have to be some magnitude. We'll call it Y1 at an angle of 0 degrees. And the only way that can happen is for these two terms to cancel out. That's the only time that the impedance, the admittance, Y, would have a phase angle of 0. So if we rewrite this as 1 over R plus J times omega C minus 1 over omega L, so it looks like then we would like to have omega C minus 1 over omega L equal to 0. That's the only way we can have a phase angle of 0. So if we look, we'd have, that says omega C has got to equal to 1 over omega L, or C is 1 over omega squared L. So now we can do the calculations. We'll have 1 over 500 squared times the inductance of 10 millihenries, and that gives us a capacitance of 400 microfarads.